Hi everyone, it is the final exam and they really did put your exam right at the end of all this bunch, didn't they? Thanks WJEC for really elongating the exam season this year, but there we go. We are in the last final stages of it. I know that a few people have been having a bit of a panic that this exam seems like a lot. Now, yeah, I agree, but I also think there's a little bit of worry because of the way they've chopped this unit up. It's not normal, it's bizarre, but that's because this unit often contains some synoptic content. And what that means is it could contain content from the other units, and certainly a bit from AS sometimes. Let's fingers crossed they don't do that this year, but that's probably the reason that it looks like there's so little chopped out of this. The reality is that there has been a good chunk chopped out of it because the bits that have gone are quite sizable. And the bits that are left are most likely going to be asked as a cross-reference to another question. Let's have a look at what I'm talking about because I'm just blathering on a little bit here at the moment. So here we go. In 2022, this is the accommodations that they have made for this unit. And Unit 4, remember, is a unit that covers a big chunk of the really cool computer science stuff. So this is what they've said. And you may notice this is slightly different to documentation you've seen as well, because the version that's available on the WJEC website clearly was copy and pasted from last year because it's still got 2021 in it at one point. This is the version we get as teachers. And the breakdown of the units that are removed is essentially hardware and communication has been removed from it. The input, output, the networking stuff is huge. There are some basic things about system architecture and stuff that we did at AS, that we did at GCSE that might pop up, but hopefully we'll just be knowing the key concepts. They're likely to ask a question if they ask one at all there on assembly language, but we'll take a look at that in a minute. The other one is Unit 6, the operating system, and good because that section is huge. Memory management, buffering, and scheduling is not the most exciting thing in the world, so that's been removed, which is great. And then the need for different types of software systems and their attributes. Unfortunately, what they removed from this one were the types of software that I think are easiest to revise because they're the ones they've asked past paper questions on in the past. So you may have noticed if you watched my video from the other day that I did go through some past paper questions on those topics just to show you the types of questions that you might get. The problem with this is that some of the types of software that they do ask you to know about are very vague and strange and not particularly helpful. Now, the rest of the content, all great. And if you've got the rest of the content done, and let's take it like a punt. If you've got the rest of the content done and 1, 6, and 7, you've pretty much ignored, you're probably going to be fine. 1, 6, and 7, there's some key things, and fingers crossed they ask them cross-reference other questions. But if they do ask them as standalone, I've got you sorted in this session today. But let's get started because we've got 400 slides to cover. And last time it was an hour and a half. I'd like to go under an hour and a half today if we can. Here's our topics. The bits in bold are full topics. So let's start with a partial topic, which is hardware and communication. Now, this is basically how the CPU works. From GCSE, these are the 3 key components of the CPU. The upside down trousers is the ALU, the arithmetic logic unit. It's the bit that works out the maths and the logic. That's all you really need to know about it. The registers are the fastest pieces of data that are on the CPU. We'll break them down in a minute. And the control unit is the bit that controls the clock cycle. It's the bit that's going next. That's what controls the fetch, decode, execute cycle. That's the bit that tells the next instruction to be pulled from memory. The registers then are exciting because there's a couple of key ones that you need to know about. The program counter, which points to the next instruction, the accumulator, which stores the result, the CIR, the current instruction register, hint, hint, stores the current instruction, the MDR, the memory data register, stores the data, and the MAR, the memory address register, stores the address. I mean, these things hopefully are self-explanatory. You could learn more about them than that, but hopefully you won't need to know much more than that. In this case, the PC and the accumulator are things that are actually used in assembly language, which we'll talk a bit more about in a minute. But you don't need to know any assembly language per se. You need to understand the idea of it because they give you the assembly language instruction set in the question if they ask you a question about that. So that's registers. Let's zoom back out. There's our CPU. That's the bit of the computer that does the processing. How does it communicate? Through buses. Buses are essentially cables. They're very thin traces, really, not necessarily cables, very thin traces on the circuit board that allows these things to communicate. You can use the Year 7 sarcastic answer for this. What does a data bus transmit? The data. What does the address bus transmit? The address. And what does the control bus transmit? The control signal, the next. That's the key bit that we have that works with the CPU. CPUs as well have cache memory because registers are very, very small in capacity. There's not a lot of space there. And registers are going to store all the instructions of the program that we need to work on. So unless we want to get it from RAM, which is quite a big process, we want to get it from a cache, which is a local storage. The bigger the cache, the more likely I am to have a copy of the instructions that I'm looking for. The smaller the cache, the less likely I am. We can do parallel processing as well. If a CPU's got more than one core or more than one CPU, but cores more than likely, that means for every core we've got, we can do another instruction at the same time. Single core on the left, quad core on the right. So if I can chop a problem down and make it parallelizable, if I can spread it out and make all the parts of it work at the same time, take the output and stick it all together, then this, and a very simple idea would be you take the time and divide it by 4. Sounds great. That's not how the real world works though, because not everything is parallelizable. And that's where AMDAHL'S law comes in. Now, my class, I know you've seen this with Mr. Chung, and I know you sort of went, it's not that bad. It is something you can bring into it. We haven't seen a question ever with AMDAHL'S law in it. So it's unlikely that we'll see one tomorrow, but it is worth. Some questions come up. Do we need to learn this? Do we need to learn AMDAHL'S law? Look, it's theoretically, it's in your specification, right? It's in a section of the unit which has been chopped out. WJEC are usually very good at giving us formula when we need them. Usually, they're pretty good with that. Let's be honest, they are. They're pretty good with that. They give us a lot of description about this. I wouldn't worry too much about it. If you really want to know it, I'd be repeating it to myself and writing it down on my exam paper when they say go, because it's very, very straightforward and it's nothing too complicated. Basically, if you want to work out the time it takes for a process with, for a parallel processor to work out the execution time of a process, you need the number of time it takes normally. You also, which is T1, you need N, the number of cores, and B, the fraction of the algorithm that's sequential. So let me give you an example. If T1 is 6 hours, so on a single core processor, it takes 6 hours. I want to work out what it will take in a 12-core system, but where 80% of the code is sequential. In other words, 80% needs to be done start to finish. So roughly speaking, I mean, you could roughly just estimate it at 80% of the overall, but let's have a look. So we replace the numbers here, and what we're looking at then is working out blah, 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 blah. You can go back and pause this and watch the VOD if you want to, but essentially we're getting this 4.89, or basically 4.9 hours, isn't it, for it to execute, which sounds about right if you do it in your head. Roughly speaking, look, if it says 80% sequential, in your head, 80% of 12 times time. That should give you a rough idea. But AMDAHL'S law is a great way of working out the exact thing. I don't know whether you need to know that formula off by heart or not. The specification doesn't specifically say you need to know AMDAHL'S law, but AMDAHL'S law is how we were to work those things out. I would suggest, and don't take my word for it, because I do not work for the WJEC, I'm just a teacher. I would say, if you are at this point freaking out about this, don't worry about AMDAHL'S law. If a question comes up on it, multiply the numbers together and give me a rough answer, and you'll be able to answer the rest of the question from there. Right, so that CPU is plugged into RAM. RAM is your primary storage. That is where all the instructions that you're currently using are stored. So that's all the open programs on your computer. Anything that's not open but is still stored will be on the secondary storage device, the hard drive or the SSD. Now, that's great. Where does your cache come in? Well, your cache comes in connecting the CPU to the RAM. And we sometimes have multiple levels of cache. So you have a bigger cache, then a smaller cache, then a smaller cache going towards the CPU. Bear in mind that even the smallest cache there is bigger than the size of the registers. So data is flowing from the hard drive to the RAM, then from the RAM to the cache, then from the cache to the registers. And that's pretty much how it's working all the time. As well as that, we've got our input and output devices to control the signal, and that's essentially a computer. Now, there's a diagram that I think is reasonably straightforward, but this is the diagram that the WJEC like you to draw if they ask you about it. You've got that diagram of the CPU, you've got your memory and your input and output devices, and then you've got a bunch of arrows that, to be honest, it's just a bit confusing. The key thing is the control bus goes from the control unit to the input device, the output device, and that's it. Then we've got two buses that are unlabeled going from the CPU to the memory and back again. That should be a reasonably easy diagram if you want to have a look at it. Okay, so assembly language. Assembly language you've done before. Assembly language is something that's in the GCSE syllabus, so you should have looked at it. You certainly should have. At the GCSE syllabus, you need to learn these things. You do not need to learn this. This stuff that's on the screen now, you do not need to know to take into the exam, because every past paper question, they've given you a different type of assembly language, which is fine. But I just want to very quickly go through a standard kind of assembly language and show you what's happening. You've got your input and output commands, which take values in, puts them in the accumulator, and takes values from the accumulator and sticks it on the screen. You've got storage. Data is just, there's some data here. Store, STA, sticks it in the stores it in the memory, and load, sticks it in the accumulator. Add and subtract, what might they do? What a surprise. And then a control instructions. Halt, stops, branch or jump will move you around. Branch on 0 means it'll only jump if it's on 0. Branch on positive, it means it'll only jump on positive. Now, this stuff I'm only talking about, I'm going to stop for a second, please, because I can see the chat freaking out a little bit. If you've not done this stuff, don't panic. This is one of the things that is not mentioned as being removed. They traditionally do a standalone question on this one, which I've shown my class when we were in person. But this stuff might not necessarily come up in that question as a standalone. It might not. I would hope it wouldn't this year, because of the way they've structured that accommodations document. But you never know. This is just in case. So let me give you an example of one in action, how it works. And once you see it work, it'll be straightforward. This is a times table calculator. Here's a series of instructions. Look at the things on the screen. We've got a program counter that always points to the next instruction, and an accumulator, which always stores the result of the answer. Okay, so when we say go, we fetch. Fetch means we get the instruction pointed to by the program counter. Our program counter is pointed to 1, so we fetch that. And the first thing we do is we increase the program counter to point at the next instruction. I decode, so that means, what does IMP mean? It means input. Okay, let's do it. What number is the user typing in? The user's typing in 9. 9 goes into the accumulator. Smash it. I'm in the way of the program counter, aren't I? Let me go down there. So I'm going to go in the way of the fetch, decode, execute cycle. Right. So with the execute done, we go back to fetch. Now what fetch does is it goes, right, let's look at the program counter. Let's see where we're going next. We're going to 2. Okay, so I go to 2, and then I increase or increment the program counter. Brilliant. Okay, I need to decode that instruction now. Store in 7 means take the value from the accumulator and stick it in line 7. So what's in line 7? Line 7 is that. So that number from the accumulator is going to replace the number in there. Boom, save the value. Okay, next one. Load from line 8. Okay, so what's on line 8? It's 0. Load that into the accumulator. And notice it's a very straightforward process. This is not a complicated thing at all. It is very repeatable. You just need to see it working to get an idea of it. We're going to add 7. This is the key thing. We're not adding the number 7. We're adding line 7. Okay, so we're going to add line 7 to the accumulator. Line 7 is 9. 9 plus 0 is 9, goes into the accumulator. Output shows the accumulator on the screen. Let's see that. Boom. Okay, now here's the next one. BRA is a branch instruction in this. it might be a jump instruction for you. We'll have a look at a proper question in a minute. Branch to 4 means we set the program counter to 4. Watch the program counter when I execute it. So I'm decoding it, branch to 4, executing it, watch it, because it's currently pointed at 7, 4. Okay, cool. So that means when I fetch, it says go to 4, basically a loop. Right, okay, so let's keep going. So I'm going to bash through this. We add another 9, that's 18. We output that to the screen. Cool. We branch to 4 again. So we're going to loop back, essentially. Okay, then we're going to add from memory location 7. That's another 9. So that's 27. We're going to output it. We're going to branch back. And this is an infinitely looping program, so this will go on forever. We go back up here, and we can do that forever now. We're just adding 9 to it and outputting the number over and over again. Now, as well as that, there's labels. Labels makes it a bit easier to do that program. Same program with labels. On the left-hand side, you'll see that you've got the labels for the lines. Line 4 is the loop line. Line 7 is the table line. Line 8 is the start line. And then on the other side, instead of saying store on line 7, it's saying store in the table. Instead of on line 6, go branching to line 4, it's saying branch to the loop. So it makes a bit more sense how that's all going to work. Okay, so what the computer is doing basically in the background is converting those to numbers and dealing with the code normally, but for humans, it's a bit easier to read. Here is an example of a past paper question on this. They've always in the past given you, as you can see there, a series of assembly language commands. In this case, they're completely different in name and structure to the ones we've just looked at. That's fine. They change them up every year. They're different every year. If you see this question, it'll be different again. So we've got in here load RX, which means load register R with a numerical value X that puts a number into it. You're basically going to be reading through this and looking at what tools you've got to put things together. Then write a program to input a number of daily rainfall readings. They love rainfall readings for some reason. For a weather station, ending with a rogue value of -1. Rogue value basically means a value that's completely different to what I'm expecting. You wouldn't expect negative rainfall. Rain wouldn't be sucked out of the ground and brought back into the, well, I suppose that is at the water side. This isn't a chemistry exam. But we wouldn't have a negative rainfall reading. So a rogue value basically means a number we're not expecting that will tell us we're done. So -1 will tell us we're done. So the mark scheme is this. We basically start at 0, start our readings, and start inputting. And the key to this is the jump. Okay. The jump loops us back there over and over and over again until we can output our total, because we've got this JNG, which is jump if the contents are less than 0. So once I've taken my input, if the content's less than 0, I jump to finish, which is past the jump point to take us back there. So if I get a negative value, I jump to the finish and output everything. I'll let you go back and have a look at my previous video for that if you want to refresh on this one. But this clearly is a question that they do like. They have repeated a few times. It's not on the excluded list in the detail. It's conspicuous by its absence. It's a reasonably straightforward question to work out yourself if you need to. Okay, with that done, we're on to the proper stuff now, the full content. This is stuff that's definitely going to be there in detail. Data transmission. First thing, bandwidth. That's how much data can fit onto a medium, not a measurement of speed. Never say it's a measurement of speed. It's how much data can I put onto something in one go. 100 megabits per second means at most you can send 100 megabits of data down the cable in 1 second, but it's not necessarily always 100. If your system's working well, great. If not, tough. If we need to send 16 bits, it's going to take 1 second, no matter what's going on there. That's a bit of a lie there. The layer structure of networks, which you need to know about, deals with that in a better way. Okay, bitrate. Bitrate is the amount of bits per second that's required for an application. The higher the bitrate, the more data you need. To watch this video stream, you need a high bitrate connection because I'm sending a lot of bits to you quickly. Live lessons, video chat requires a high bitrate. Text chat, low bit rate. You need to make sure you've got enough bandwidth to support a high bit rate if you want to engage in video-based or game streaming activities. Networks. You might be given a diagram like this and asked to calculate the costs. You remember last time we talked about this, we talked about A-star search algorithm, and we talked about other search algorithms as well, which I'm not going to cover today because what we normally see in this exam is something a little bit different. So in this case, if we wanted to find the cost between node A and node D, you've got options. You could go this way, ABD, which is a cost of 6. You could go this way, ACD, which is a cost of 6 as well. So either way doesn't really matter. But if you go ACBD, the cost in total is 4. The smallest we've got there, the better. Now, normally what we do to calculate these is we use Dijkstra's algorithm or A-star search algorithm. Both of these are unlikely to come up as specific questions because they're lengthy processes, and we covered those in the previous video. If you want to go over those and have a look at the Unit 1 revision video. The VOD's still there on Twitch, and it's in the archives on YouTube as well. I've also got a nice Dijkstra's algorithm video that one of my colleagues from a different school did for the OCR syllabus, if you want to dive into that, but I wouldn't panic too much about it. So this is the sort of thing you might be asked. You might be asked to calculate the cost. Well, how do we do that? Well, the first thing we do is we start with node A, because that's our starting point. The cost to get to node A is 0 because I go from 0. How do we work out the cost to B then? Well, I'm going to say the cost to B is either going to be 5 or 4, because they are the two directions I can go. Now, which one do I pick? I pick the smallest one. So the quickest way to get to B is the cost of 4, and that's by going from C. How about C? What's the quickest way to get to C? Well, clearly, it's going to be 2 straight from A. How about D then? Well, the quickest way to get to D is likely to be coming down from B, because B was quite a short route anyway. That's a total of 5, and you can check that quite visually. And so then E comes from D, which is a total of 6. Now, calculating the cost is the simple thing to do. It's going to be worth the lowest amount of marks. What they're probably more likely to do is to ask you to make something like a forwarding table. Now, the forwarding table is broadly the same thing, but instead of it being, where did I come from in the route box, so I could go backwards and I could work out the best route, actually what we get is, where do I go to? So where do I go to from here? Okay. So the idea is all you're talking about is, which node do I go to first? If I'm going to start on my destination to B or to C or to D or to E, where do I go first? Now, you might think that's a bit of a stupid thing. Why do I just need to know the name of the first node? Well, if you were preparing a packet for a network, you would need to stick it and send, you go there first. And normally what would happen is, although they would have an idea about where they were going, that would be recalculated at every node they visited. So a forwarding table is actually really important for network traffic. The last bit of this is always a bit weird. It's like talk about the internet, and they've never asked a question. There's not a lot of detail on it. The only thing we can really say about the internet is that it's a network of networks. It's a worldwide communications infrastructure. It's made up of computers using roughly the same protocol, which is TCP/IP, and connected using various hardware and connections. Well, great. The key differentiator, as far as I'm concerned, is that you need to know the difference between the World Wide Web and the internet. The internet is the communications infrastructure behind all the things you do online. It is what is making it possible for this video to be streamed, for web pages, and the chat to be going on in the background. But the World Wide Web is only web pages, and that's really important that you get that distinction. The World Wide Web, www, is simply web pages. It was invented in the 90s by a British guy called Tim Berners-Lee, and it is sitting on top of the internet that allows us to use web pages. So next one, data representation. Time is ticking away here. So data representation is the biggie, because this is where you are going to be asked to do these things. I'm not going to cover these in this video because these are things that you've been doing since GCSE. Certainly my class, if you want to grab, go into Google Classroom, you'll find all my worksheets and stuff on that still there. But you've been doing this for ages. You did this for GCSE, you did this for AS, you doing it again this year. The most likely questions that you'll have are things like this: describing the difference between 2's magnitude, sign and magnitude, and 2's complementation. Now, what does that mean? Well, sign and magnitude is a way of representing negative values by using the most significant bit, or the leftmost bit, just as a negative identifier. If I put a 1 in there, that means it's negative. The only problem with that is that I lose the range. It gives me 2 zeros. It gives me a positive 0 and a negative 0. So that's not great. 2's complements are much better. Basically, the most significant bit is the negative version of itself. And that means that we have the full range and only 1 0. It does make the maths a little bit harder, though, because when you're working out what's going on here, you're adding up a negative number. But 2's complement is usually the way forward and is the way you'll have your floating point arithmetic questions usually set up. So do be aware of that. I've also got a video on this exact thing called negative binary or something like that. Anyway, it's on my channel. Have a look at it. It's before the year 13 videos. It's only got about 20 views. So, you know, push those numbers up. Let's get monetized. But if you want a quick refresher on all that negative binary stuff and why it's the case, go back and have a look at that. Okay. Right. Okay. Right. Now, floating point. This is a big thing. Floating point calculations, they will tell you how many bits are in the mantissa and how many bits are in the exponent. Now, the mantissa is a normalized representation of data. And what that means is if it's positive, it's going to be 0.1 something. And if it's negative, it's going to be 1 point something. The reason for that is it's 2's complement. The most significant value is a negative indicator. So if it's negative, the leftmost value must be a 1. And if it's positive, the leftmost value must be a 0. That's what normalized means. Therefore, the mantissa is important to be normalized. Okay. The exponent is how many places do we move the decimal point, the binary point, and in which direction. You've done this before, I'm sure. It's a very straightforward procedure to how that works. I've got a video on my channel again if you want to go and repeat that, but you've practiced this a bunch of times. This should be straightforward for you. Questions will give you different size mantissas and exponents. The more bits you get for mantissa, the more accuracy. The more bits you get for exponents, the larger the range. The problem is that both of these values are stored in one word space. So one instruction would store both. So that means that if I increase the size of the mantissa, I'm going to have to shrink the size of the exponent. And if I increase the size of the exponent, I'm going to have to shrink the size of the mantissa. So it's a balancing act. How much range and how much detail do you need? They also like asking you about truncation and rounding, the difference. Truncation is where we basically just drop the decimal. Rounding is where we actually round it to see what's better. Now, rounding is computationally expensive. It takes a while to work out. Truncation is very computationally simple. But the problem is, in this example here, if we truncate 36.6, it's going to take us barely any time, but it's going to give us an answer of 36. If we round it, it's going to give us 37. Rounding is certainly more accurate, but it's going to take us longer to get to. And it's always important that you don't do this until right at the end. You never truncate or round data in a computer system till you're about to show it to the user. Otherwise, you can get order of magnitude errors. Imagine that this was like, I don't know, how much of an ingredient do we need to make 100 cakes? 36.6. If you truncated or rounded it at the start and then multiplied it by 100, you'd either get too much or too little. The best thing to do is multiply it out and truncate or round the last value, because you're only going to be a decimal point out. Logical shifts. Okay, now there's a big difference here. We've only really ever talked about shifts before, but there's a difference between logical and arithmetic shifts. Logical shifts, we shift all of the data right or left, depending upon how many times it's told us, and we replace the gaps with 0. Remember, as they fall off the bit pattern, they disappear. If I'm doing a left logical shift by 3, it needs to move to the left 3. The easiest way to do this on paper is cross out the 3 values on the left and write in 3 zeros on the right, because this is happening. It's moving 1, 2, 3 places to the left. We've got a space, some of it's gone, so we're bringing in the zeros. The question is, what's a shift function? That's what this is, okay? Arithmetic shifts work the same way, but if we're shifting left, we fill with 0. If we're shifting right, we fill with whatever was in the most significant position. So if we're going this way, if we're going to the right, this value here is what will fill up the empty spaces. So let's do it. So a right shift by 4 will move all the data 4 places to the right. And again, if you do it on paper, cross out the 4 on the right. So 1, 2. Why is it filling with 1? Because it's an arithmetic shift. An arithmetic shift, as it moves, fills the gaps with the leftmost value. That gives you a more realistic answer than replacing it with zeros, because that is going to be closer to what the multiplication would have been. Okay, just remember that all that shifting is doing is multiplying and dividing by powers of 2. But there is a big difference between arithmetic and logic shifts. But you need to remember that if you do it to the right, you divide by 2 each time. If you do it to the left, you multiply by 2 each time. That was actually a question on the GCSE paper this year. So they've got that in their heads that they want to ask people about that. Okay, overflow is a common thing that you guys know about. If we're doing a binary addition and the amount of bits we need to store the answer is more than the amount of bits we've got available, then we lose that overflow value. And the reason for this is because this isn't normal maths. This is us doing mathematics in a computer system where we've got a fixed amount of registers, a fixed space, a physical space to store that value in. If the word space is, in this case, 8, I can't store any more than 8 bits. So the moment it goes above 8 bits, I lose the most significant value. So what that means is that this is essentially 181 plus 172. But because I haven't been able to store the most significant one, it's given me an answer of 97, which is completely wrong. But that's what the computer's doing when it overflows. Now, there is a concept called underflow as well, which is quite important and often misunderstood. Underflow is when a shift results in a number that needs more than the available bits. So basically going the other way. The number becomes too small to represent, not too big to represent. In this example, if I'm shifting to the right by 2, it moves once, it moves twice, and I've lost that 1. It's disappeared. It's gone from my registers. That means, despite the fact that this is a really, really small fraction, the best I can do to represent it is 0, and therefore I've lost some precision. I've lost some data. An underflow is where I lose it to the right because of a shift, and an overflow is where I lose it on the left, usually because of binary addition, but sometimes because of a shift as well. Okay, 4, not doing bad for time, actually. Organization and structure of data, big one. First thing, serial and sequential files. New records get added to the back of a file, to the end of a file in chronological order. Old stuff, new stuff, new stuff, new stuff, new stuff, new stuff. Okay, very, very straightforward. It's the same as opening a file in append mode in Python, and they are used where the order is not important, the number of records is small, or most often the data should be stored in chronological order. So most sales systems do this because it's a good idea to have the most recent sale at the bottom and the older sale at the top. Sequential files then add their records in specific orders, so more like databases. There's a sort going on as data comes in. And that's important sometimes because we really need to make sure that we keep data in some sort of order if we're going to have efficient searching. Indexed files are where we have that sequential style, so they're sorted, but they're ordered by a key field. Now, we can set what that key field is, or we can create our own key fields, but that makes searching easier because something like binary search will get to the record in quicker time. Inserting a record, though, becomes more difficult. It's not just a case of going in at the bottom. Inserting a record means we need to find out where it should go. put it in, move everything else around it, and it's a bit of a problem there. So that's more processor intensive, but for searching, which is probably the more common use case for an index file, it becomes much, much quicker. Then we've got the idea of a master and a transaction file. And this is very, very straightforward. Again, the idea is this: if I've been adding to a file for a long time, the file's probably huge. If the file is in the region of terabytes, then opening it to add one thing to it could take forever. So what we do is we have a copy of that file with nothing in it, that's in the same structure, the same style, the same layout, and that's what I add to throughout the day. This gets a bit bigger through the day, but it never gets as big as the master file. And then maybe overnight in a batch process, it copies everything over to the master file later on, and the transaction file is empty again. It's just a quick way of storing data when we've got loads already stored there that we need to care about. Hashing algorithms, and we talked about this from the last exam as well. What they normally do in an exam question for this is they give you a hashing function and ask you to work it out. Remember, the key idea of hashing is that we're going to take any kind of data and represent it numerically so that we can store it usually in an array. You need to be able to store data in an array in a sort of a sorted way, and that's what a hashing function does, and be able to search it as well. So let's have an example. In this algorithm, it's very simple. We take the number of every letter and add it together. So if we're going to add test, we get the word test. Every letter is given a numerical value. It is added together. We get 64. Now, clearly, on the right-hand side, there are not 64 elements in my array, so I need to mod it. In other words, get the remainder of a divide by 16. That gives us 0. So that means it's going to go in position 0. Boom, done. Okay. We're going to add another one. I'm going to add high. Do the same thing. We work out the value of each letter and add it together. 17. Mod that 16. That's going to give us 1. That goes in position 1. So it's just sort of finding like, well, a reference. Where would that go? So if I'm going to search for it later on, then I can do that. Now, if I put P in, that's one letter. It's 16. 16 mod 16 is 0, and we have an issue. We have an issue because it needs to go in the same place. So normally what happens is, in a simplified hash algorithm, it goes, oh, there's nothing here. Let's just keep going down until we find a place to put it. Or I can't put it there because there's something there, so I'll put it here. So worst case scenario, if I'm looking for P, I'll look in 0 and go, oh, it's not there. Oh, but there's something next to it. Is that it? No. There's something below it. Is that it? No. There's nothing below it. I haven't found it. So that's how we use a hash algorithm to find things. If we're looking for high, for instance, we just rehash it and find it in 1. If we're looking for Mr. M, we get the hash of that blank row and we can't find it. Reset would wipe all that out. The question is, and in this particular paper, the key thing is that you need to compare the algorithms and you need to talk about time complexity. So how long is it going to take, and space complexity. And we talk about those in terms of big O that we looked at for the last paper. You need to be asking questions like, how many collisions occur? That means how many times in this table is a piece of data likely to hash to the same one? If you look at the past paper questions, that's what they're all about. There's an algorithm purposefully designed to have loads of collisions, and you need to stop that. How evenly is the data distributed as well? If you've got 10,000 spaces, are they all bunched to the top? Because they should be spread throughout it. And that's how you write a more efficient comparison algorithm. This is a classic question as well, multi-level indexes. Indexes, basically, instead of having 20 million records, an index for all of them, we split them up into subcategories. I'll show you an image in a second to remind you. The idea is that we have an index that takes us to one level, an index that takes us to another level, and an index that takes us to where the data is on the disk and it finds it. The key thing to remember when we look at this image is these indexes are not created until they're needed. So here's the obvious example, okay? If I'm going to insert 32 into there, I create an index from location 20 because 20 to 40 is where 32 is sitting. Whoosh, goes into the second one there. That gives us a bit more detail, and you can see there's a bit more detail in that. We're going 20, 25, 30, 35 than the first level. Okay, but this one goes into 30 because it's 32. So that goes into the third level, and that gives us a more precise breakdown of the 5 areas that I can go to there, and I'll have the physical location stored. The important thing here is that the second and third level are not created unless they're needed. So there is no second level table at the moment for 0, 40, 60, or 80 because there's nothing stored in there. And by doing this, we keep the storage space requirements down and only add to it as we go. So here's a question. Explain how a multi-level index works when searching for number 56. So let's say I'm looking for 56. Well, first job is I'd find the first level, which is closest to without going over. Okay, so 40 is the closest one. That would point me to a second level table here. In the second level table, I'd be looking at the number that is closest to without going over, which is 55. That would point me to a third level table, which then has the physical location. I then go from there to the physical location on disk and get the data for the number 56, whatever that might be. It is important that you remember that there's that steps involved in there. Questions on this very often like you to break that process down for them. Overflow in a hash table then. What happens when indexing is full in a random access file? Well, first of all, if it can't be stuck in there, we stick it in an overflow file. And all an overflow file is sequentially stored. It is like, oh, our clever process didn't work. Let's stick it in a file just in the order that it came in. Now, we could be clever and we could rehash everything and make more space, but we need a larger file. We need a larger hash space for that anyway. So let's have a look. Notice my hash table on the right is full. What happens when I want to add A? Well, first of all, A is hashed. A is 1. 1 mod 16 is 1. It needs to go in 1. Oh, it's full. It would then proceed to look through all that table and eventually go, oh no, this table's full. Great. So what does it do next? Well, it does this. Okay, here's my overflow table. Stick it in the top. Doesn't matter what it hashed to, just stick it in the top. That is how dumb overflow is in hashing. And you might be looking at this and going, what's the point of this? What's the point of this at all? What's the point? In reality, hash tables are pretty good at making big piles of data easier to insert, easier to find, quicker to find. And it would not be a size 16. It would be millions of records long. So it'd be much more efficient than that. And then the overflow table being sequential wouldn't necessarily be a problem. A question that's popped up that is worth picking up. The chat's a bit weird today. So this is a good question. What's the point in it being sequential if it's in chronological order anyway? You don't always want data in chronological order, see? That's the thing. A serial file will be in chronological order because it's just the order they're stuck in at. That's that kind of file. If you're talking about a sequential file, it will be sorted. When it goes in, if you say, I want an alphabetical order, for instance, the entire file will be rejigged. So every new thing going in ends up in proper alphabetical order. So it would be about how I want it sorted. That's the point of a key field in a database. Right, how are we doing with this? Question from one of my students, how early will I be in school tomorrow? As early as I can, but I will certainly be there by 8 o'clock. And I'll go straight to my room for you guys. You can come in and revise for as long as you want to before the lesson tomorrow. Okay, 5, another full topic here. So we're doing quite well. Now, databases, key topics here. And hopefully most of you have used databases in your project anyway, in your NEA, in your coursework. So hopefully a lot of this is not new to you. You've used databases. So you've got a better handle on what they are than last time you ever would have been asked about them. First of all, the point of databases is that we want data consistency. We want them to be validated. We want them to be indexed. If I look for a date of birth, I want it to be in the same format as anywhere else. And if I've got multi-table queries, and I know that we built a bunch of multi-table queries. Do you remember we were doing those left joins and bringing tables together? Well, when we're doing multi-table queries, you don't want the entire thing to stop if one of them breaks. So if one of the multi-tables doesn't work, we want to be able to go back and make sure that nothing has changed. There's not part of the database changed. We also don't want data redundancy. I don't want to be storing things in multiple places everywhere. If I'm storing your name, I'm storing it once in the database and linking it, because otherwise I'm going to get problems. I also want data independence. I want the data to be separated from the programs that access it. And this is why when you built something. You probably built your database in something like MySQL, or you built your database in Microsoft Access or something like that. And then you built the software for it in a different language. So my class, we built it in PHP, but you may have built it in Visual Basic. I feel sorry for you. There's not enough hot showers in the world to get rid of this thing, Visual Basic. But there we go. You might build it in Python, maybe something like that. But certainly you would have a separate program to build the interface and the logic than you would storing the database. Here's an example of a flat file. It's basically an Excel spreadsheet. Don't write that in an exam, you get 0 marks. But basically, everything's stored together. See, there's data redundancy. The names are being repeated. See, there's inconsistency in it and the way we're storing things. So we don't want that. So normalization. Right. Okay. Reality is you can probably jump to third normal form like that. You may need to show the stages. First normal form, each field only contains one item of data. So you'll notice back here, I've got things like, have I got anything with multiple lines of data in? Maybe I haven't. We'll have a look in a second. But normally it's like names. You'd have all the parts of somebody's name or address in one place, and we want to split those up. Also, all the attributes must be dependent on the primary key. What does that mean? That means you group the tables by their theme. Let's have a look. So in this example, I'm splitting them up roughly like this. I've got information about teachers, I've got information about students, and I've got information about subjects and rooms. All right, well, that means they should really be 3 things. That's first normal form, because in each table now, the data is all dependent upon the topic of the table, in this case, the primary key. I've added some primary keys in at the start, unique identifiers, and none of those pieces of data are non-atomic. They're all separated out into the smallest possible parts. Okay, second normal form, it's got to be in first normal form first, and it has no partial dependencies. Well, what's a partial dependency? Well, have a look at this one. In this table, we've got the number of we've got the students in there. Okay, well, why is that important? Well, students have been enrolled in a class. Look at how many times I've put the same class down, computer science, 11A CS, just to get student 1 and student 2 in there. If I separate that table out and I call it something like enrolled, there's no data in it apart from other IDs, but it does link those things together. There's now no partial dependencies. No table has data that's not really related to the topic. Third normal form has no transitive dependencies. So transitive dependency is like this. There are only 3 subjects, but I could theoretically have more computer science lessons. Therefore, that's a transitive dependency. It is dependent, but it's not necessarily dependent upon the class ID. So we split that out. I've ended up with 5 tables, and that's third normal form. There's another transitive dependency there, though. Room. Room is not necessarily linked to the class. So let's split that out as well. And notice I've put links in there for everything as we go. Then you might need to do an entity relationship diagram. You did this in AS, in the practical exam. You did this actually in your programming projects. Remember, there are many entity relationships, but only one really matters. One-to-one is where one table is linked to one other table. Really happens. Many-to-many, where many records from one is linked to many records in another. You can't computerize that. That's impossible to computerize. So that doesn't really exist. In third normal form, what you're looking at is mainly one-to-many relationships and maybe the odd one-to-one. What does that mean? Well, in this example, we're saying that one student can enroll in many classes. The way I like to think about it is if you follow the direction of the arrow, the pointed part of the arrow is where the drop-down menu would be. So if I'm enrolling a student in a class, I'm going to pick a student from a drop-down menu. I'm not going to be entering the student. I'm not going to be picking the enrollment from a drop-down menu. I'm adding a student. One class can be in the enrollment many times. In other words, I'm enrolling a student in a class. Click the drop-down menu, pick this class. Click the student, pick this student. Nice and straightforward. One subject can appear in classes many times. Again, if I'm creating a new class, I'll pick the subject from a drop-down menu. One teacher can appear in the classes table many times. Again, if I'm making a new class, I pick the teacher from a drop-down menu, and the same with rooms. I'll be picking it from a drop-down menu. Okay. First normal form is not necessarily one table. Okay. First normal form is usually multiple tables. They're split off into their own constituent parts. So I'm struggling to click on the correct one, the one to show. Yeah. First normal form is not one table. Okay, first normal form is likely to be multiple tables, but it could be if the examiners ask you something like that. Okay, there is a topic on validation and verification, which I'm not going to go through because you've done it a million times, but just a reminder, your validation in blue are things that can actually check it looks right. Verification are things that check it is right. Make sure you're discussing the proper thing, please. Now, SQL, SQL, you must know, because not only will they ask you to read it, they'll ask you to write it. You really need to be careful with the SQL because most of you will have written some of it, okay? But it is just remembering the syntax. And this is the sort of stuff that I'd be going over as I was walking into the exam. This is what I'd be going over in the minutes before I get called into the exam hall. So just try and remember the structure of that, okay? So this is how you create a table. In this case, I'm creating a table called teacher. I'm making sure that there's a key field called teacher ID, which is an integer. The first name is text with a maximum size of 128 characters. The salary is a number. Numeric, not really a type, but this is what the WJEC spec says. It can have a maximum of 7 digits with 2 decimals. A date of birth is a date time, which is date or time. And then an email address, which is 256 characters, not null. That means you can't leave it blank. Then finally, you say what the primary key is. This is actual valid SQL. You could type that into MySQL and it would build that table for you. So then you also need to be able to search for things. The way we search for things is with the select query. Select star or asterisk from teacher means show me everything, every field from the teacher table. Then you can customize it, where the salary is greater than 50,000 and the first name is Peter. So we can join things together with ands and ors, and we can use greater than and less than and equal to get all those comparisons going. You've probably written these before. You'll be asked to write individual searches. You might be asked to only return specific fields. In that case, instead of the asterisk, you list the fields. Select the email and the first name. So I'm only going to get those 2 things back from teacher with salaries greater than 50,000 or it's less than 30,000, and then order by salary ascending. That means we're going to start with the lowest salary and go up in increments until we get to the biggest salary at the bottom. Okay. You need to know all this stuff, all this stuff. How do we add records? Well, it's going to be the lazy way, which involves this. Insert into teachers, put this into the teachers table, these values. And then in brackets, the values just have to be in the same order that your create table was in. If I go back just for a second, they're in the same order as these. Their ID, the first name, the salary, the date of birth, and the email. Let's check that. ID, name, salary, date of birth, email. Okay. You do need to be careful with this because they will always ask you to insert something. So you've got to sort it out. Okay. Updating, that's changing a record. Update this table, the teacher's table. Set this field to this value where the teacher's ID is this number. That's important. If you were to forget the where bit, it would change everyone's date of birth, the 1st of the 10th, 1975. Not ideal, really. These are also the bits of SQL that haven't managed to sneak into everything else. We're going to have in, which is basically, we can use it with the where command to give a list of options, or secondary query. So we could do another query within it. So we could go select star in something if you wanted to. Group by means that you group the records based on a field, and then all the inequality symbols, less than, greater than, all that sort of stuff, and stuff like that. Right. Nearly there with this topic. DBMS, database management systems. These are pieces of software that manage your database, shockingly. It's the interface between the data and the processes and the access that's needed to use it. And one of the key things about it is it adds different levels of access. So this might be how we're storing something in a database management system. And you notice there, we've got things like key fields and types and lengths and validation all built in because it allows us to access that data. Finally, topics like big data. Big data is where we're using data sets so large that it becomes difficult to process it. I'm not talking about large in the scale of a school here. I'm talking about every transaction or every click anybody's ever done on Amazon. If we can analyze that and that data set is huge, we'd know masses about everyone. And they do. They do. That's how they make suggestions to you. Data warehousing is a way in which we use lots and lots of storage arrays to be able to store big data because it can't just be stuck on a hard drive. Data mining is where we analyze large amounts of data to come up with trends. And then the final one is predictive analytics, where we use statistical techniques like modeling, machine learning, and data mining to work out what's happening. So all these things are really important. All these things are this concept of big data, where we're analyzing huge data sets, come up with ideas to help our companies or to help our products. Distributed systems as well are a little bit different. This is where we're going to be storing data across multiple computers. This is really important in databases because we need to store data across multiple computers because databases are huge. Distributed processing, though, is where we get a process, and just like we do with multiple cores in a CPU, we split it up amongst multiple computers across a network. And this works really well if we've got hundreds of computers that we want to split data up and do a small bit with. It means we add resilience, we add security, and we add scaling by doing both those things. So if we want to be able to, a few computers to go offline and still to get what we want, resilience is what we want. If we want to have more security on everything, this is the way to go about it. And if we want to scale it, if we want to be able to deal with big data, this is what we need. Okay, 3 more to go. Get in there. 2 partial topics. The operating system. Operating system is a bit rubbish because it's sort of like, what are they? And again, AS, GCSE, you've done this stuff already. Batch processing. It's where all the jobs are saved up and they're in a similar format. And then maybe at the end of the day or at the end of a certain time, the computer flips modes and processes them. The best examples of this are calculating energy bills. They work out your energy bills once a quarter. They just store up your usage in a big file and then slowly work through them and work out your cost. Bank transactions work in the same way. Single user operating systems are probably what you've got at home. It's where one user can use your computer at a time. You can log off and somebody else can log in, but only one person can be on that computer and that operating system at a time. There's multi-user then, where more than one person can be on consistently. Multitasking is where a computer is moving through all the different applications so fast it looks like it's doing more than one thing at once, which is what all computers were until we got multiple cores. And then I wanted to show you this past paper question because this is where we talk about multi-programming and multi-user operating systems. Now, the mark scheme for that is multi-programming, multi-user operating systems are where we have one computer with a load of different users, that's the multiple users, running separate processes, that's the multi-programming part, from different terminals. In other words, there's a bunch of computers all connected to one big mainframe computer or big server. Users can log into that at the same time from different terminals, and each of the terminals are processing different things based on that main computer. You can go through the video to watch the rest of that, but they are the key topics in operating systems. The other thing that might be in there is this idea of interrupts. Now, the idea of an interrupt is very, very simple. I'm using my computer and I press a key on the keyboard. Well, that probably means I want something to happen. I want something to go into there. Sorry, there was a question there. Doesn't this mark scheme talk about stuff that was taken out? Yes, which is why I haven't gone through it in ridiculous detail there. That mark scheme for that previous one, if I show this one, is talking about scheduling, which is not there. Okay, but there are parts of it that may be questioned. Again, apologies if you find these past papers a bit confusing with this partial unit. They do tend to ask questions based on multiple things, which is why it's difficult with the past papers to find one that only looks at the bits that aren't being covered. Okay, right. So interrupts, press a key. We want the computer to go, hold on, a key's been pressed. What are we doing with it? Rather than just go, I'll deal with you later, get to the back of the queue and carry on loading your web page or whatever. So the mark scheme for this is reasonably straightforward. What is an interrupt? Well, it's a signal sent to the CPU that action is required, and it might be made by hardware or software. Straightforward. Okay, and 2 instances where an interrupt would be generated and what it would do. Well, key presses. Okay, pressing the key on the keyboard causes the CPU to go, oh, what's happening with this key? Where do they want this A to go? Probably into the word processor. It might be activating a menu with a click. It might be loading something from a disk drive. There's a bunch of options there. Go review them. Go have 1 or 2. But the key one, the most obvious one, is an interrupt. Press a key. I want something to happen. Press a mouse button. I want a button to click. Press an A. I want that to go into my word processor. Okay, here's a question here. How likely do you think it will be that they ask a big mark essay on something from the partial topics? At this point, guys, I don't know what to suggest. WJC have been doing some really strange stuff with the questions. Unit 2 GCSE exam was just I honestly don't know. I can only hope they'll be fair to you. I think the partial topics are probably indicative that they're probably going to include them in other questions, or may use similar styles to what we've looked at in a few of them. I mean, I wouldn't be surprised if the assembly language question came up in its entirety, which is why I did that in class with you guys, those of you that were there. The other questions, there's less of them to talk about, so they might be partial to other things. It's difficult. It's difficult. I'm not really sure what they've done. I imagine what they've done, by the way, imagine what they've done is that they have used the paper from 2021, so last year's paper, and what they did with that is they had it written, so they just published a list of, oh, these are the questions we're not asking you things about. So, I mean, you can read it one of two ways. You can read it, there's definitely going to be a question on these subsets, or the questions on those subsets are not very important. And I think most of us teachers have read they're not going to be too important, which we can only hope is correct, because that's the way most of us have been dealing with it. And do you know what? If that's not the case, then everyone's going to be in the same boat anyway. Okay, right. Dealing with interrupts. Okay. An instruction joins the queue. It has a priority number associated with it. If the priority is higher than the rest of the stuff in my list, what I do is I dump my list into a stack. I just go, ugh. I deal with the interrupt, and then Siri was getting involved then. I deal with the interrupt, and then I pull my instructions back from my stack and carry on working through them. It's a great way of being able to dump and resume things quickly. Okay, 2 more to go. Good timing. I've got a meeting at past, so I need to get this done by past. We'll get there. Okay, this partial unit is a nightmare. I've had people tweeting me about this. I've had people getting confused by the videos. There are only a couple of past paper questions that cover this topic at all, and most of them are about the things that have been taken out. So, what's left? Well, I've got this question here, and I've got this in my video, not because expert systems is going to be in there, because it specifically says expert systems is not going to be in there, but to show you the sort of question that you might get. This question might appear, you know, if they might ask you about a piece of software for a couple of marks. I wouldn't have thought what's left in this, it'd be an 8 marker, probably maybe a 4 marker, something like that, if they ask you it at all. It's most likely that they're expecting you to understand different types of software to ask you a different question that incorporates types of software. Those combination questions are common in this paper, and that might be why they've had to sort of say, and there's only a bit of this and only a bit of that. That might be the reason. So anyway, expert systems are widely used to describe the benefits. Whoosh. Big load of the benefits to the organization. And it's a big topic, so there's a lot of things you could think about there. Okay, let's see if we can apply that same question to this topic. Wide and local information exchanges. If you watch my video on this, you'll know that I don't really know what that is. It's a term. If you Google it, right, you get generic stuff. There's nothing in the textbook. There's nothing in the specification, as far as I can see, about these two things. So what I have here is my best guess about what these two systems could be. I think what it is most likely is a way of exchanging information with other similar organizations on different scales. So for instance, schools often share information with each other. That would be a local information exchange. I would be sending information from my school to your school, and there'd be data that was shared. In a similar way, we do that with a local authority. We're in the Vale of Glamorgan, so we as a school send information to the Vale of Glamorgan about attendance and grades and stuff like that, that all the other schools do as well, and the Vale of Glamorgan work out some data and some stats. That could be local information exchange. What's wide information exchange then? Well, I imagine that's when local authorities share with each other across the country. Maybe they share with central government on a bigger scale. To be perfectly honest, I don't really know what they're trying to get at with just this heading. It is a very vague term, and there's no detail. Again, if you've seen detail, pop it in the chat. Let me know. I can't find anything or any detail about what these things are supposed to be, so that's my best guess. No guarantees on that, I'm sorry. Then search engines. You know a little bit about search engines. You might be like, what is there to know about search engines? Search engines are just things like Google, right? You type something in, you get results back from the internet. Search engines look for the content on a web page. Oh, right? Search engines look for the content on a web page. What does that even mean? What does that even mean? Well, I type something in, it gives me the pages back, doesn't it? What more do you want there? Well, there's more. Okay, how does it do it? Well, what it does is it indexes the web. It has little things called spiders, little programs that go off and look at all the contents of the web and looks at links and who's linking to who and what page is linking to where. And what it does, it builds up a map of the internet as a result of that, or a map of the World Wide Web more properly. And then it uses what we call a page rank algorithm. And what this does is it gives each page a number on how important that is. Okay. And that page, the rank of the page is very much based on how important the pages are linking to you and how important the pages are that you're linking to. That sounds weird. How do you know those two numbers? Well, it's because the algorithm is recursive. It keeps running and running and running and running. And if it finds a page is really important and it's linked to you, your importance goes up. And if you've linked to that page, their importance goes up because now you're more important and you've linked to them. So page ranks are about how important different websites are, how they link to each other. Then the very vague part of the specification says you need to understand contemporary software. This is a very vague word, contemporary, when the WJEC is speaking about this, because they mean things like this: presentation software. Don't use the brand names, by the way, but just to give you an example, something like PowerPoint showing this sort of stuff on the screen. Desktop publishing like InDesign or Publisher, making things that should go on paper. Spreadsheet software like Microsoft Excel for calculating numbers and working out cost forecasts and things like that. Drawing, things like Illustrator or Photoshop. And the difference there, Photoshop is bitmap editing, which means we edit the individual pixels, and Illustrator is vector editing, which means we edit the maths behind how it's created. And they are specifically different. Database software like MS Access or MySQL allows to store the database. In fact, they're database management software, so they're a specific piece of contemporary software. Animation and 3D rendering software like Animator from Adobe, Maya, 3D Studio Max, there's a bunch of them. They allow you to create and render scenes. And then there's a topic on mobile apps. I mean, I don't know what generation would be better pressed to answer questions on mobile apps than yours, to be perfectly honest. But you might be asked to explain what a mobile app is and how it works, or at least know what it is, and apply that to another question. Great. I love this topic. It's so vague as to be useless. And then there's a heading in the specification that says, what is the effect of the internet on professionals and the community? Now, this is one of those things that you probably know. I mean, how has the internet affected people? Well, wow. Okay. So one, you don't need to memorize things anymore. We still test that, don't we? Because you're trying to learn a bunch of stuff for the exam tomorrow. But in your real world, you're better off having a skill like data analysis or application of the knowledge than just knowing the knowledge. The way you communicate is different. Synchronous versus asynchronous communication. In other words, do we do like this, where I'm talking to you and you can talk back to me? Or like the rest of my videos, asynchronous, I've recorded it, I sent it out to you, you watch it when you want. Web or social presences are needed for all businesses in loads of different areas. I mean, doesn't matter if you're interested in TikTok, you probably, if you're a big brand or you're a reasonably sized service, you probably need a TikTok presence. You need to manage that brand to make sure it's not being tarnished online and improve your page rank for your website. The last one there is one of the big issues in community and the professionals is proving plagiarism. Okay, so plagiarism is a really common thing nowadays because the internet allows for it. And how do you do that? Is it easy, and does it even really matter? Last topic, and it's an actual big topic as well, so we can do this in 10 minutes, I hope. So you remember, this is quite a complicated thing, and they normally ask really random and bizarre questions on this one with a lot of maths involved. So go and have a look at the past paper questions for this, again, all on my YouTube site. But when databases, files, and infrastructures are online all the time, we need to be careful with security there, because updating things online means that we have external access to files, which means that if we can get unauthorized access to files, that data can be corrupted or changed. There's a big difference between accidental and malicious data. And of course, the difference between hacking, which is the process of smashing your keyboard with your sunglasses on and try and break into a computer, and social engineering, where I call up and pretend to be somebody else. So I put a high-vis jacket on and walk through security. There's concurrency, which is checking in and checking out files to making sure that I'm not double booking a flight or a seat, and backing up data and making sure those backups are valid as well. Okay, cryptography. Cryptography is the process of transmitting encrypted messages so that when you intercept them, you can't see them, which is probably exactly what I want to be happening to the chat at the moment. I'd rather not be reading what was actually there. I hope this is the best revision you're going to have, guys, honestly. Oh, my goodness me, because the chat is a bit crazy. But encrypting means that if I send a message to you and somebody sees it en route, that is nonsense to them. Encrypting data means that the only person that should be able to decrypt it is the person with the decryption key or the password. And a really obvious example of this is the Caesar cipher, where we move letters on a number of spaces. And that's a really easy one to break as well. A Caesar cipher could be calculated like this. You have the value for the letter and the offset, and you mod it 26, you modulate it 26, so you give the remainder of dividing it by 26, which means it goes back into the alphabet. My class, please remember, if you're doing this, write the alphabet down on top of your paper. You are not good at remembering the alphabet contemporaneously. Write it down on the top of your paper so you can check it. If we're doing a Caesar cipher with an offset of 4, we'd take out the value of A, we'd add 4 to it, shift it across 4, and it'd become E. The problem with it is it's really easy to crack because some letters repeat more often than others. English has a very specific structure, so it's very easy to break. There's an idea as well of symmetric versus asymmetric keys. A symmetric key would use the same encryption key and decryption key. If I know the password, I can encrypt the data and decrypt it. That's a nightmare because that means that both ends of the transaction need to know the same password, and if any of those leak, we're knackered. If you break the key, you can pretend to be me or whatever. Now, asymmetric encryption means that I have a different key to you. I can encrypt my data and you can unencrypt it, but you can't encrypt data in the same way I can. Both of those are not easy to work out. Public key encryption is great because public key encryption would mean that top secret data passes through a public key and becomes nonsense encrypted data. In order to get it back, I can't pass it to the public key again. It's asymmetric. So I can use your public key to encrypt any data that I see. If I want to unencrypt it, I have to pass it through the private key that only I have, and I can see the result returns to being readable data. Now, this paired encryption method, public and private key, means that I can leave my public key on the internet for everything else, keep my private key on my device, and between that pair, I can let anyone encrypt data. I can encrypt data myself. Anybody else can encrypt data and send it to me, but only I can look at what was sent. That is amazing. How do we compare methods? Because one of the questions, obviously, that they have in an exam is compare them, which is better and why. Well, the first thing is how easy is it to break? If it's easy to break, it's not great. The other one is how computationally expensive is it to encrypt and decrypt? If it's taking a long time and a lot of resources to encrypt and decrypt, then it's probably not great. There are methods of cryptography. For instance, if we turn the amount of bits in public key encryption up to I don't know, like 2048 bits, it would take days to encrypt and unencrypt a piece of text. So that's too much. But similarly, if we used 2 bits, it would be broken in a few minutes. So we need somewhere in the middle, and we're about 256 bits at the moment for AES encryption. How logically complex is it? Because if it's too complex to work out in your head, you're probably going to program it wrong. So if you're going to program it wrong, best not to use it, because if you program it wrong, there will be security vulnerabilities and they'll be picked up. This commonly happens. If you make something too complicated, people will build poor versions of it, and then the encryption is broken anyway. Is it symmetric or asymmetric? Asymmetric's best. And how many keys are necessary? How many different keys do I need along the chain to get it to work? Now, ideally, it should work on all kinds of data without corrupting the original. And the encrypted data, or the cipher, should be no bigger than the original, because if it becomes bigger than the original, then it seems a bit pointless. Biometrics. Okay, just a reminder, biometrics is the measuring of biologically unique features, things like fingerprints, things like eye scans, facial ID recognition. You all know of my terrible, terrible relationship to our friend Gru from when I was showing you this in our lesson time. But when we use biometrics to measure things like the shape of your face or your fingerprints, there's a very tiny, tiny chance that you'll have a match with somebody else. However, it is technically possible that you could have a match with somebody, especially especially uh, identical twins have issues with this as well, where there are some elements of biometrics that would match up to them. If you pop questions in the chat, I will try my best, but we'll have a questioning time the last 5 minutes, okay? Right, fingerprint and facial recognition is a basic feature of most smartphones, and we have passports that include that stuff. Advantages: more secure, faster to access in most cases. It can't be forgotten. You can't forget your face. You can't forget your thing. Well, you could, but it would be a horrible accident that caused that to happen. And you can't be socially engineered out of your fingerprints. Again, yeah, it depends what the biometric is. Disadvantages: some conditions it's unreliable, right? There are some areas where a biometric could be unreliable. I'm wearing a mask because of a pandemic. Oh no, Face ID doesn't work. I'm wearing gloves because it's cold. Oh no, fingerprint sensor doesn't work. There are privacy concerns with us having your data about this, and biometrics might change due to age or illness, especially if you're doing something like voice print identification. You get a cold, it won't recognize who you are. Okay. So, biometric data can be difficult to capture, encode, and store, and it's only recently that we've been able to do that quickly and easily. We don't store your fingerprint. We don't store your face. We store the mathematics of it. And because of that, we can process it quickly and easily and push it in. The problem with it, though, is because all this can be done automatically, this stuff is done at concerts. Facial recognition is applied en masse at football matches and things like that. And people that look dodgy, I say look dodgy, not to humans, to the computer system, are pulled out of the crowd. So that's not ideal. Okay, malicious software, categories, viruses, they replicate and they damage. Worms, they replicate, they might enable remote control. Trojans break into a system, pretend to be something good, end up being something bad. And spyware, look at what you're doing and share that information with somebody else. Okay, we have 3 types of hackers. It's problematic language, but we're dealing with it hopefully. Black hat, white hat, and gray hat hackers. Black hat hackers intend to do damage. White hat hackers have been asked by a company to break in and to make their security better. Gray hats are trying to break into a company to make their security better, but don't have permission. The ones that go to jail are usually the gray hat hackers because they're not trying to hide their tracks, but they are still doing damage. Now, penetration testing, pause for giggle normally, is the process of hacking where a user or white hat hacker is asked to break into a network and then report back the findings so it can be fixed, or it can be patched, or it can be made more difficult. And that's it. Oh. Now, Unit 4 is huge. Unit 4 is allowed to contain synoptic content. Unit 4 uses questions where multiple topics are sometimes overlapped. It's a big topic. It's a big unit. But if you looked at the past paper questions, they repeat formats year after year after year. We probably will see things like a floating point question. We probably will see things like calculate the hash value of this, draw a diagram that explains a 3-level linked links, you know what I mean, a 3-level link thing. It's late. All those things are things that you would probably see. Go and have a look, please, at my past paper questions. And good luck for tomorrow. I think we might all need it this time. It's going to be a weird exam. WJEC have done some odd things with the exams so far this year, but at least this is the last one, and we can have a little break now until we see the results. Try your best. Make sure you try and answer every question, and just remember that you're 13. When you're doing your answers, they go straight into an answer booklet. There's no format given, so you will have to write everything out and plan out your marks yourself. Make sure 1 mark per key unique point. Right. I'm going to attempt to go into this ridiculous chat for a moment, see if there are any genuine questions in there. Let's have a look. Doesn't look like there are. Lots of questions for my hairline, but unfortunately it's on the back of my head, so I can't get that far back on the camera for you. I do apologize. The stages of penetration testing. I didn't put it in my presentation. It is one of the past paper questions that we have seen. It is worth jumping onto the past paper question videos that I've got on that. If you're interested in that one, worth a go. Final prediction for topics. I really don't know. I imagine that all the things we had in bold, data transmission, representation, organization, databases, and security, there's going to be a big question on all of those. I expect to see probably a question where you are working out maybe an encryption, one of those questions, where they give you an encryption methodology and you work it out, a mathematical one, maybe a hashing table one. I think that would be an easy one. The three-level structure type diagram would be an obvious one to put in. But again, you saw the last paper. They've been doing some random stuff. All we can do is hope for the best. And I really am struggling to think what they could ask some of these questions are, because in terms of what they've taken out big chunks, then left partial bits hanging around. And I imagine the partial bits are being used in the big essay questions and things like that. But we'll see. Right. We've got 4 minutes to go. I am going to disappear so I can at least have a quick drink, because I haven't managed to get through much of my water in this hour and a half before I go on. A quick question. Does third normal form come up a lot? It does often. You're given tables and you're meant to go through them. But I tell you something that's almost guaranteed, and I say that, I don't work for WJEC, remember, is the SQL questions. They love to ask a question about third normal form. They love to ask a question about SQL that are worth a big chunk of marks. It is worth going through those before the exam. Guys, all I can say is do your best. Okay, my class, I'll be in my classroom as soon as I can tomorrow, probably about 8-ish. I'll just go through whatever you want me to go through, be that past paper questions, whatever. We just go through it for an hour before the exam. Do make sure you bring a calculator with you, because if you're doing WJEC, you are allowed a calculator. If you're not doing WJEC, not so much. So good luck to you. But WJEC, you definitely are. So make sure you bring that in there. Grade boundary predictions, low. That's all I'm going to say, low this year. I hope this has been useful for all the random people in the chat who were just talking about random stuff that I'll never look at again. But certainly for my class, I hope it's been of some use to you, and I'll see you guys tomorrow. Good luck to everyone. Please make sure you don't stay up all night just to try and stick this stuff in your head. Computer science is as much about problem solving, and to problem solve, you need a clear head. So please make sure you get to bed at a reasonable hour and get a decent amount of sleep, and don't panic too much. At this point, it is what it is, and we're all in the same boat because we've all been given the same information. Okay? Good luck to you. Try your very best. That's all we can ask. And hopefully you get the grade you need to go on where you want to go next. Thanks very much for tuning in. I'll see my lot tomorrow. Everyone else, good luck.